I'm Tim Ventura, and we're joined today by Dr. Timothy Andersen, Principal Scientist at the Georgia Tech Research Institute. Tim is a nationally recognized researcher in high-performance real-time signal processing and machine learning, and a Doctor of Philosophy in Mathematics, which he received from Rensselaer Polytechnic Institute, with an emphasis in computational physics, Markov Chain Monte Carlo, and high-performance computing. Tim's academic research in quantum gravity focuses on quantum Kaluza-Klein theories, and he's published over 200 articles on theoretical physics, mathematics, and the philosophy for the infinite universe on Medium, as well as on aeon.co and Substack. So Tim, welcome. Thank you so much for joining me today, sir.
Great to be here.
Today, we're talking about an article that you wrote, A 5D Theory May Explain Quantum Entanglement. And I'll put links to this. This is on your Medium blog. So this is related to the 2022 Nobel Prize in Physics. So let me begin by asking, what motivated you to write this article?
So what motivated me was the Nobel Prize came out, and I've been working with this 5D theory for a while. And what I wanted to see was how entanglement would play into that theory, which I hadn't really thought about that much. I haven't done any research into it. And one of the things I like to do when I have a new idea is actually to write an article about it, to get my thoughts in order on what's going on here. So I'm hoping to do more research in that area, but that was the motivation, was the Nobel.
Yeah, well, I mean, it made headlines around the world,
Mm-hmm.
right? And so again, I do a little bit of research for these. Nobel Prize in Physics 2022 was awarded to Elaine Aspect, John Clauser, and Anton Zeilinger for quote unquote experiments with entangled photons, establishing the violation of Bell's inequalities and pioneering quantum information science. And I actually stole that right from the Nobel Prize website. But from what I've read, from what I understand, their work actually reinforced a lot of existing science that had come before, right? So is it okay to ask, what is it about their research that's creating so much media attention?
So what I thought was that the Nobel validated a lot of what the research had done. So it was in sort of a statement that's saying, yes, the scientific community has come to the consensus that what they had shown through these experiments is valid, and we should all accept it. So in that sense, it was a validation of what they did, but it also gave a huge amount of attention, as the Nobel always does. And because entanglement is such a favorite topic for science popularizers, because it's such a strange phenomenon, I think those just kind of snowballed into a huge amount of media attention. Unfortunately, what ended up happening is a lot of people thought this was a recent confirmation of things that had only been theoretical, when in fact most of the experiments have been done in the 70s and 80s. And so we were very well certain that that entanglement was a true phenomenon.
Okay. Well, that makes sense then. Now, one area, and this comes out of past interviews that I've done, that it seems like there was some disagreement over, is this concept of superluminality in entanglement, right? And as I understand things, so that the measurement of one particle affects the other instantaneously, faster than the speed of light. But from what I've heard, this can't be used for communications because of something called the no communication theorem. And again, this is kind of the gossip mill, I guess, as it were. But what I've heard is that there's kind of like a gentleman's agreement between relativity and quantum physics over the no communication theorem, but there are actually a small group of people who believe that that's not true, and that it's just kind of a way of, wrapping up loose ends. So
there's no reason to believe, and in fact, there's no experiment that's ever been shown that you can communicate between two particles via entanglement. And the reason is really because it's actually relatively simple. And I think I can use an example. to show how that's true. If you imagine you have two dice, right? And these dice, whenever they're thrown, they always show the same number up. Okay, so if one says 2, the other says 2. Now, you give one to your friend, you keep one, and then you throw the dice, okay, and it says 3. Now you know that your friend's going to see 3. All right. Now, suppose I want to send information via this dice to my friend. Well, I would think, okay, suppose I take my die and I set it down on 4. Will my friend then roll the die and see 4? They won't. That's how quantum entanglement works. Is as soon as you try to force some information into one particle, it breaks the entanglement, and the other one is going to become disconnected. So that's why you can't send information. It's always going to be random, and the only way that you can know what your friend measured really is to compare notes.
Okay. Okay. So I want to get in again. I'm going to dig deeper into your article because what you're proposing now is a 5-dimensional model of entanglement. Actually, this is what got me really excited about it. But so for the audience sake, I guess, let's dig in. Can you explain kind of what you mean by 5D, right? Is this a physical dimension that we're talking about, or is this just kind of a mathematical parameter to make the math easier?
So I'm proposing it's a physical dimension. So there's actually a long history to this, which is that starting in really in the 1950s, this goes back a long way, there was a method of doing quantum mechanics, quantum physics, that was called stochastic quantization. And that's just a big word for meaning that we could imagine a quantum system is like taking the whole universe, time and space, and imagining it randomly sort of moving in a fifth dimension. And that method of stochastic quantization assumed that that fifth dimension was simply a mathematical parameter introduced for convenience. My proposal was to take that and really, 70 years worth of research, which is a bit fringe in quantum mechanics, and say, well, suppose that is a real dimension. And now, what are the implications of that, both to quantum mechanics and also to, general relativity and how we understand dimensions to work. So then that just sort of automatically means that, yes, we have to be living in a 5-dimensional universe.
Ah, okay. Well, and so let me get into, I'm going to jump around on my questions a little bit, but for folks who aren't familiar with this idea of higher dimensions goes back quite a ways. One of the first that I wrote about was Einstein's unified field theory. He had the metric torsion tensor. He was playing with some ideas of higher dimensionality. And that came out of just feeling unsatisfied, right? With, I think, some of the same things that you're talking about, these, this spooky action at a distance and things like that. Later on, I think this was the 50s, there was Kaluza-Klein theory. And I believe you're a Kaluza-Klein person, right?
Yes.
Yeah. And oh yeah, go for it.
So yeah, Kaluza essentially came up with, and I think this was actually in the 20s, but he came up with this theory that if you just added an extra dimension to Einstein's general relativity, which is a 4-dimensional theory, that you could then unify Einstein's relativity, which is a theory of gravity, with electromagnetism. And so he made a bunch of assumptions and he said, okay, if you make these assumptions, for example, everything has to be the same in that fifth dimension, like nothing ever changes. It's called the cylindricity assumption, because it's kind of like our universe is a circle and then it's like a cylinder in that fifth dimension. And if you made these assumptions, then you could unify those two theories. And Einstein got super excited about this and said, well, we'll unify all these forces. And then, of course, someone came, well, where is this fifth dimension? And that's where Klein got involved. So Klein said, okay, suppose this dimension's actually really curled up like a little straw, you know, and so we can't see these because they're real tiny, and it's sort of like you have like a carpet with a bunch of little loops, or something like that. And then they were able to show that yeah, we can unify electromagnetism. But then when they started to go to other forces, they ran into all kinds of problems. And that's how we got string theory. Was basically they took some of what Kaluza-Klein had done, and then they added strings to it. And instead of having the dimensions themselves create forces, they had the strings do it. But anyway, so people have been playing around with these extra dimensions for a long time. And the main difference between what I've been doing and that is I'm not trying to unify with any of the other forces. I'm purely looking at this five-dimensional manifold as sort of this universe as a way of both of unifying quantum mechanics, some of the weirdness of quantum mechanics with space and time, as well as I'm looking into some implications for dark matter.
Ah, okay, okay. Well, and it's interesting. In one of Michio Kaku's books, I think it was the one on Einstein, and Kaku was involved with the development of string theory. He had said that one of his inspirations to get involved with this was actually he had said that when Albert Einstein died, they had on TV, I believe it was, a photo of his desk, and on his desk was the unfinished manuscript for like the final version of the UFT. And he'd said, he wondered what was in that, and that was one of his inspirations. And as you'd mentioned, that later on you had string and brane theory, and I believe they increased the dimensionality, right? They were talking
Correct.
about 9 or 11, and as you'd said, everything came back to a string, or in brane theory it's a membrane. um,
Right.
it seems like those kind of come and go in terms of favor in science, right?
Yeah. So string theory, you have basically like 11 dimensions if you accepted a supersymmetric, which means that every particle has like it has like a partner particle. So electrons are what we call fermions, and they would have a partner, which is a boson. Anyway, so and then if you didn't make that assumption, then you've got 26 dimensions, which but who knows? All of these multidimensional theories have no real. They're mathematical. They have no experimental basis for saying that they're true or not. And so while physicists introduce all kinds of higher dimensional theories, the emphasis, in my opinion, needs to be on making those predictions and being able to confirm that's there is actually an additional dimension.
Yeah. Yeah, well, no, that's an excellent point. And again, these do seem to come and go. I remember like picking up, science magazines, and it was like string theory, and then a few years later, they're like, okay, nobody talk about this. So
That's true. And string theory has, I mean, it's gone through phases, and there have been some really interesting mathematical results that have come out of string theory. What hasn't come out is any kind of unified or grand unified theory. And a lot of people have said, well, we need to sort of move on, but the problem is that other than string theory, there really isn't another grand unified theory that has ever gained any traction. So that's partly why so many people are still so I think attached to it.
yeah, yeah. Well, and this entire idea, I mean, like entanglement itself, which is really your focus in this paper. This
Mhm.
is such a big topic, right? There's so much to this on itself. One of the other aspects of this that you were talking about was the Copenhagen interpretation,
Mhm.
right? Because this spooky action at a distance, this raises all sorts of these big uncertain questions. And
Mhm.
if I understand correctly, in your paper, you do not subscribe to the Copenhagen interpretation. You're saying that that's probably not true.
So the Copenhagen interpretation is, and I've actually done a lot of reading about how it came about, and it emerged from trying to figure out how to explain these different experiments. And honestly, the Copenhagen is a way of understanding the experiments from really the experimenter's point of view, in that we have a model of particles as basically waves that sort of expand in space, or they flow through space as these sort of extended objects that just fill the universe. But then when we make measurements, we only see that one we only see the effect in one spot, and that's the particle, right? So it's like if I send, a photon, which is a particle of light, through some space, it will be like a wave expanding, and then I'll try to detect it, and I'll just get it at one point. Now the Copenhagen, the way that they interpreted this is that when I go and make a measurement, this wave that exists simply collapses. It's like, it's spread out. I go and look, and it's boom, one spot. And somehow it's either, depending on what kind of Copenhagen you subscribe to, it could be it's because I'm a conscious being and my consciousness is, and then you get into sort of mystical aspects of it. Or it could be that it's interacting with measurement apparatus and that somehow causes a collapse. In any case, one of the problems with Copenhagen is that it inherently says that there is information loss in quantum mechanics. And information loss is expressed in quantum mechanics. It means it is not unitary, and unitary is really just means that it conserves information, which means that the parts of the wave function you do not observe cease to exist, or maybe they never really existed, depending on how you look at it. And some people are okay with that. Roger Penrose was okay with that. But in my mind, it's a very inelegant way of looking at it. And so many people gone to things like the many worlds interpretation, which is a unitary, meaning it preserves information. And my version is not that different from the many worlds interpretation, because I have like different events spread out in a fifth dimension. And there are some proponents of the many worlds, for example, that who have interpretations very similar to mine.
Okay, and now in your case, this fifth dimension, and this is kind of a manifold, I guess we could probably describe it that way. Is this cylindrical? Because you'd mentioned in the paper that it's a little bit like time, but with time, since we're moving through it, we can kind of look back, I guess. With this one, it disappears behind us, and so we're moving through it, but we can't see it, so to speak.
Yes. Yeah, so the idea here is that you have a four-dimensional universe, okay? So it's made of space and one time dimension, three space dimensions. And this is flowing in a fifth dimension, as if it were another time dimension. Now, whether it's more like time or more like space doesn't really matter, but it's similar to how we experience time. The reason why we don't experience it the same way as time, in the sense that we remember like previous events and things, is because in this fifth dimension, entropy is actually already maximal. So that means that basically we remember the past because entropy is always increasing, and entropy is really just an increase in the information content of the universe. So more information means that we can contain the past, the memories of the past, in the present. And as we go to the next moment in time, now we can contain another moment. And so we keep adding to that and remembering more and more. And of course, we can't remember the future precisely because it has more information content than present, okay?
Mm.
Has more entropy. In this fifth dimension, the entropy is maximal, which means that essentially nothing really changes. It's sort of like if you were to walk through a room where the air is very still, you know, and you would find that the air doesn't really change. And that's because it's all like equilibrated, okay? That's what the fifth dimension is like. Our time dimension is more like you went through a room where it was very cold on one end, like a hallway, you're coming from outside in the winter, and it gets warmer and warmer. And so you notice that change, you know?
Okay. Okay.
So that's the difference. There's like a gradient in our time dimension, but not in that fifth dimension.
Yeah. And so in this entangled dimension, I guess, and this again, this comes back to the spooky action at a distance. If I understand this correctly, basically these particles are touching. This is a local action in that dimension, right?
They're not exactly, I wouldn't say they're exactly touching. I think the way I think of it is that in time, in four dimensions, a particle is basically like a little string. Okay, so it's like this, we call it a world line. In the fifth dimension, that string then it becomes like a sheet. Okay,
Okay.
so it's and that when you have two particles that are entangled, that means that they basically, it's like they're sharing a sheet. Okay, so even though the world lines appear to be separated, they're actually connected together in the fifth dimension. But it's not so much that they're touching. They're still like they're touching in the past, of course. Like that's how they're created together. They're touching in the past, and that whole sheet, you know, sort of interacts. You know, so it's like you can imagine that you have these world lines like a little Y. Make a little Y. So they're like that, right?
Yeah.
And they're flowing forward, and this is sort of changing, right? And that's how they become essentially correlated with one another. Is those world lines kind of change in that fifth dimension, and of course that happens like very very quickly, but that's how they become correlated. It's not really that they're touching; they're not actually like this in the fifth dimension. It's more that they're part of this extended object that can change in a dimension that we cannot see.
Ah, okay. Well, and it's interesting that you describe it like that. Actually, I did an interview, I think 2 days ago on retrocausality, and what he said was actually similar to that. His focus was on time, but he was
Mhm.
talking about the particles being created, and I believe in his case, he was saying that interactions can go down and then come back up, and that avoids some of the superluminal aspects of it. So.
Mhm.
So now in your case, well, I think what you're saying is that it's dimensionality that allows those
Mhm.
particles to interact.
Yeah, it's that flow that allows them to interact in
Y-
that fifth dimensional flow.
Yeah. Well, I'd like to ask, what kind of capabilities do you think, and this goes directly to your expertise because you have
Mm.
such a heavy background in computing and information processing. With a 5D model, do you think that may give us capabilities for quantum computing, quantum communications that we haven't had before?
I have thought about it a little bit. I haven't really come up with any like clever technology that might utilize it, but I have often thought about if there is, you know, potentially some way of manipulating the fifth dimension. Now, in my mind, because I tie it to Kaluza-Klein theory, I imagine this manipulation is sort of similar to how you would manipulate it to create like a gravitational wave or something, you know, or a little warp bubble or something like that. Some kind of change in the fifth dimension. Because if quantum phenomena is part of this 5D manifold, then that 5D manifold obeys the laws of general relativity, which means that energy and matter influence the shape of that manifold. And so there's a potential to use gravity in ways to manipulate quantum behavior, which I think would be really cool, but probably well beyond our technology.
Yeah, yeah. No, that makes sense. Well, for the time being, right? For the time being, but in the future, we may get there.
Mhm.
Well, Tim, let me thank you so much for your time today. And thank you so much for describing a lot of the principles behind this. I'm going to put a link in the YouTube notes to this article, as well as, the other things that you've written. You have a
Mhm.
tremendous amount of work. I would love to have you back on in the future to talk about some of the other things you've done. Um, for today, let me close by asking, what comes next for your own work? And do you have any thoughts on continuing work on this 5D model of quantum entanglement?
So my work right now is actually to try to find ways of confirming the model. And so one of these is to tie it to some of the observations we've made that we attribute currently to dark matter. And so how does a Kaluza-Klein theory, create potentially dark matter-like effects? And so hopefully, by going very large, we'll be able to bring it back to the very small.
Wonderful. Thank you again so much for your time today, sir.
Thanks for having me.